now is, how much mechanical energy does an orbiting body have? This is a body that's in orbit around a central big body, a central mass. So I'll make the central mass, actually should make this radius go straight to the center. We have a central mass, I'll label it big M, and we have an orbiting mass, I'll label it little m. And if it's orbiting, then it's going to have an instantaneous speed that's tangential to the orbital path. And don't get mixed up. You look at this and you're like, oh, that's like a Bohr-Rutherford diagram. And there's other people that look at the next diagram that we're looking at here. They're like, oh, it's like Bohr-Rutherford diagrams. It's like electron excitation from chemistry. Well, if you want to borrow that concept a little bit to help your brain feel better, you can borrow it a little bit, but it's really not the same thing, right? Like we know that electrons don't orbit in circles or ellipses. They orbit in complicated shapes that are actually kind of probability waves that look like balloon animals, and we all just accept that, right? And you guys know what I'm talking about with SPD hybridized orbitals. We are not talking about that with these guys. We really are talking about circular paths and elliptical paths because these are planets, not balloon animals or chemistry orbits, okay? So when I have this thing, don't tell the chemistry people I said their things look like balloon animals. I think that like don't you guys think like a P and a D orbital look pretty cute though? I think they look cute. All right. So we know that this object, if it's in a stable circular orbit, F big G is going to be equal to F C. We expand that out. GMM over R squared, that's universal law of gravitation, is equal to centripetal force mv squared over R, where the little m's are the orbital bodies. Now, I want to hold myself back. I don't want to cancel the m's. I know you're like, it hurts to not cancel the m's, but I don't. I don't want to cancel the m's this time. I want to keep that m. There's a reason for it. What I do want to do is cancel out the R. And so what I can say is mv squared is equal to g mm over R. And I'm just going to have to stay there. And the math people in the room are like, no, I need to simplify. No, not this time. Okay? I can see the pain in a couple people's eyes. All right, so we're going to leave this as equation 1. And you know what? I think I'm going to use my highlighter a little bit. I'm going to highlight those. And I'll tell you why I'm going to highlight them later. But right now I'm just going to highlight them a nice pretty pink. And I want to remind myself of another thing that we said once before. E total is equal to 1/2 mv squared plus negative g m over R. I'll put brackets around that. I want to call it equation 2. I'll put a box around it. And I think I'm going to pull my pink marker out again. mv squared. Ooh, look at that mv squared. Isn't that so cute? See how it shows up in 2 places, right? So what I want to do is sub equation 1 into equation 2. I know that it's common to sub in like for one variable, but you can do this. This is allowed. And so what you can do is write E total is equal to 1/2. Instead of writing mv squared, I'm going to write GMM over R. That's allowed. Plus, the same stuff that was there before, GMM over R. And you're like, I see what you did there, a little shell game. Swapped out some stuff for some other stuff that kind of looked like the stuff that was there already. You see what I mean? It's almost like this little switcheroo made us have some like terms that didn't look alike before. And it's important that we can do that. It's very tricky. It's not obvious. So if I now have these like terms, I can say I have a half of this mess minus a whole of this mess. That means that I now have negative a half of said mess. Oh, that really did clean things up a lot. And so if somebody were to say, how much mechanical energy does an orbiting body have, including its kinetic energy, that one formula has it all. Even though it looks like it's just EG baked into it, Can you see that we baked in the kinetic energy too? It's really quite clever. It makes the calculation quite easy. So that's something I wanted to put out there. This is a nice question for homework problems, and I wouldn't expect you guys to have this inspiration, right? This is true inspiration. And it wasn't even my inspiration. I stole it from a textbook one time when I was learning this stuff, right? So this is an important thing to be able to recognize and even understand it. All right, here's another one. Let me write out a new question. This is the one that made me think of electron excitation from chemistry class, but it's not what we're doing now, okay? Oops. How much work? And when I say work, how much energy? How much work would it take to move this satellite to a higher orbit? And the reason this makes me think of electron excitation is that we're always talking about in chemistry getting electrons to jump to higher excitation states. Like there's the N1 ground state, the N2 excitation, the N3 excitation, or whatever for hydrogen, for example. So if you're down with that way of thinking and you know what I'm talking about right now, you're like, oh yes, I've seen these diagrams before. Show of hands in the room today. How many people know what I'm talking about? Right. Okay. So easily like a third of the room, and that's usually the percentage for a first semester physics course. By second semester, it'll be more than half the people that know what I'm talking about right now. And that's cool, okay? And you can borrow this information from physics and you can have this as a part of your well-woven knowledge of the universe when you approach it in chemistry. That's fine. But they're not the same thing, okay? Because orbital radii aren't quantized like electron radii might be, or like electron orbital energies might be. These are not quantized states. In fact, a satellite can orbit really at any orbit that doesn't have it in the atmosphere of the planet. So how much work would it take to go up to this higher orbit? Well, let's take a look at this. The work is the change in the amount of total mechanical energy. That makes sense. It had a total mechanical energy at a low orbit. Now it's going to have a different total mechanical energy at a higher orbit. And we can slap onto each of these little orbiting masses because it's the same mass. It was moving along with a certain speed at this orbit, and then it was moving along at a different speed at this orbit. Fair enough. It was at one radius for the first orbit, at another radius for the second orbit. We can call it V1 and we can call it V2 if you like. And still this makes me think of roller coasters, because when I talk about the work that we're doing here, we're talking about the change in how much the total energy is between position 2 and position 1. E total 2 minus E total 1. And what we calculated just up here was a formula, or what we isolated for up here was a formula for total energy for an orbital radius. And so this isn't even as bad as a roller coaster, I don't think. Strange that like orbital mechanics sometimes isn't even as bad as a roller coaster. So we'd say negative 1/2 GMM over R2 minus negative 1/2, I don't like these double brackets, GMM over R1. But I look at this and I say, well, I bet you I could factor out negative 1/2 GMM and leave behind 1 over R2 minus 1 over R1. I mean, I could always reverse it and use the distributive property to multiply those guys back through the brackets. But I think in this form, it's a little bit nicer. I like it in this form. Because if there's anything that I mess up, and I know that you guys mess up when you do your calculator entries, it's scientific notation. So if we can cluster together all these things as a factor out front, we're less likely to make that silly data entry. It's not a concept issue. It's a data entry issue. Now, there are other people that say, I don't like having a negative sign in two places. Could we maybe make that a little bit easier? And if you can follow what I'm doing here, this is what you would do. You'd say, okay, well, let's make it be 1/2 GMM. If I do multiply just the negative sign through the binomial, not anything else, what I would end up getting is negative 1 over R2 plus 1 over R1. And at least now the negative sign's only in one spot. But my math friends say that's not elegant enough. Nobody likes to have a binomial where the first term in the binomial is negative. And so what people will often do, and one of the reasons why I'm doing this isn't just because I love mathematical elegance. It's because you're going to see this formula in a textbook or in an online tutorial or something like that. Some 16-year-old is going to explain how they did their homework to you in a YouTube video or something like that. I want you to know why. Okay. So the reason the textbook or the person in the YouTube video, I even wrote that wrong, writes it like this is because they've already done all the legwork up above. Here, I'll even white this out so that it's really clear what the subscript is on that R. This is R1 minus 1 over R2. And that looks kind of dirty because we always think about having final minus initial. But the reason I'm doing initial minus final is because we had a factor of negative that was worked in there. And it shows up this way in the textbooks. And you're going to think it's a typo or something. It's not a typo. They just did all the simplification legwork that we just did, okay? Now, again, the textbooks often don't even leave it like that. The way they'll usually write it is work is equal to GMM over 2 times 1 over R1 minus 1 over R2. And maybe I'll put it in writing. Energy required to increase a satellite's orbital radius. And I don't think the concept of increasing a satellite's orbital radius is a hard concept, but I think you'd have to have some solid inspiration to riddle this out on your own. So that's why I think it's worth just doing a little bit of the algebra. We're not even going to sub any numbers in for this one, because since we've done all these other substitutions, these other calculations previous to this in the note, I feel like we could do this. This isn't a challenge in that way. The algebra is the challenge in this one, I think.